Picture this. Write down the numbers from 1 to 10, then highlight all the odd numbers and remove them. You're left with 2, 4, 6, 8, 10, exactly half of what you started with. Now push it to 100. Identify and remove the odds and you're left with 50 evens, again half the total. So what if you don't stop? Imagine all the natural numbers stretching on forever in an endless line. Then take away every odd number, leaving only the evens. Now here's the unsettling question. Are there fewer evens than natural numbers altogether? Instinct screams yes. Half have been cut away. So how could what's left possibly be as large as the whole? That puzzle, whether an infinity can be cut in half yet somehow still remain whole, had teased mathematicians for centuries, yet no one had found a general, rigorous way to pin it down. It took one brilliant, controversial mind to give infinity a rigorous mathematical language of its own, and to show how our common sense notions of number crumble the moment we step into the infinite. That mind was Georg Cantor. Born March 3rd, 1845 in St. Petersburg, he came from a family rooted in commerce and music. His father was a successful merchant and his mother belonged to a distinguished musical family. Cantor himself displayed serious musical talent, particularly on the violin. When he was about 11, his family relocated to Germany, where his mathematical curiosity began to take hold. Cantor studied in Berlin under some of the greatest mathematicians of the day, Weierstrass, Kummer and Kronecker, and earned his doctorate in 1867. 2 years later, in 1869, he moved to the University of Halle, where he would remain for most of his career. Halle was less prestigious than Berlin, but this didn't stop Cantor from pursuing questions that others dismissed as philosophical distractions, and it was there that he began tackling a problem most mathematicians avoided. What does it really mean to speak of infinity? For centuries, infinity had belonged more to philosophy and theology than to rigorous mathematics. The great philosopher Aristotle had drawn a sharp line. He accepted only a potential infinity, processes that can continue without end, like counting or subdividing a line, and rejected the idea of a completed infinite totality existing all at once. Even in Cantor's own century, Carl Friedrich Gauss wrote in an 1831 letter that he protested above all against the use of an infinite quantity as something completed, which is never permissible in mathematics. The infinite is only a manner of speaking. Many of Cantor's contemporaries shared this caution, treating infinity as a useful figure of speech, but resisting its elevation to a genuine mathematical object. The young Cantor refused to accept those limits. He was prepared to treat infinity as something real, an actual infinite that could be studied and compared with the same rigour as numbers themselves. That conviction set him apart and eventually brought him into conflict with his former teacher, the powerful Berlin mathematician Leopold Kronecker, who was a staunch opponent of Cantor's conception of the actual infinite, and whom Cantor later blamed for blocking his hoped-for appointment in Berlin. But at this stage, Cantor was simply following his instincts, letting logic lead him into territory few others dared to tread. When most of us think about the idea of how many, we imagine counting 1, 2, 3, 4, and so on. Numbers are how we measure quantity. For example, imagine you're given 2 bags, one full of blue balls, the other full of red balls. If you're asked whether they contain the same number, the natural thing to do is to count. You'd pull out the red balls one by one, saying to yourself 1, 2, 3, 4, and you would then continue until the bag was empty. You'd then do the same with the blue balls, 1, 2, 3, 4, and so on. And here's the point. If you reached the same total both times, you'd conclude the bags hold the same number. But what if you couldn't count? What if you didn't even know the names of the numbers? Cantor's key move was to make pairing the test of whether 2 collections are the same size. Each time you pull out a red ball, match it with a blue one. Keep going until both bags are empty. If every red ball has exactly one blue partner, and none are left over on either side, then the bags contain the same number. That's a deeper idea. It doesn't rely on reciting numbers at all. It relies on putting 2 sets of objects into a one-to-one correspondence. Or consider another example. Imagine you're about to give a lecture. A huge crowd has gathered outside, and you're worried that there are not enough seats. It would be silly to count every seat in the theatre and then count every single person in the crowd just to see if the numbers match. Instead, you could simply open the doors and let everyone file in. If each person takes a seat and at the end there are no people left standing and no seats left empty, then you know that the numbers were the same. If some people are left without a seat, then there were more people than seats, and if some seats are left empty, then there were more seats than people. These examples may feel simple, but they capture the seed of Cantor's definition. Two collections, two sets, are the same size if we can establish a perfect pairing between their members with nothing left unmatched. What matters isn't the act of reciting numbers, it's the act of pairing. Formally, Cantor turned that idea into a rule. Two sets M and N have the same size if you can pair their elements so that each element of one set matches exactly one element of the other, and vice versa. That perfect pairing is what we now call a one-to-one correspondence, or bijection. If such a pairing exists, we say that the two sets have the same size. But what exactly is a set? Well, at its simplest, a set is just a collection of distinct objects that we treat as a single entity. The objects inside are called elements of the set. We write sets with curly brackets. For example, the set containing the first three natural numbers is written as curly brackets 1, 2, 3. The set of vowels in English is written as curly brackets A, E, I, O, U. Now, the size of a set is referred to as the cardinality of the set. For a set A, we write its cardinality in the following form. For finite sets, this just means the number of elements. For example, the cardinality of the set containing 1, 2, and 3 is 3, and the cardinality of the set containing the English vowels is 5. Now, it's important to note that the order of the elements in a given set doesn't matter, and if you list something twice, it still only counts once. And here's the neat part. If we consider counting those balls again, then by Cantor's idea, when we count a finite collection of objects, what we're really doing is we're setting up a one-to-one correspondence between the objects and a subset of the natural numbers, 1, 2, 3, 4, and so on. The sounds we speak or the numerals we write are just labels standing in for those numbers. Okay, but every set that we've considered so far is an example of a finite set containing a finite number of elements. But is it possible to talk about sets that contain an infinite number of elements? What would such an example look like? And is there a way to investigate whether two infinite sets have the same size or cardinality? Cantor's great leap was to extend the concept of equivalence to infinite sets. For infinite sets, size is not about counting up to some final number, because there is no final number. Instead, size is about pairing. If you can set up a one-to-one correspondence between two infinite collections, so that every element of one is paired with exactly one element of the other, with nothing left unmatched, then those collections are the same size. In other words, they have the same cardinality. The most obvious example of an infinite set is the set of all natural counting numbers, which we write in the following form. As every child knows, if someone claims they can name the largest number, you can always beat them by replying, just add 1. There is no largest number. The list goes on forever. This infinite set of counting numbers will serve as our reference set for everything that follows. Okay, so now take the set of all natural numbers and remove all the odds. You're left with the set of even numbers, and the evens form what's called a proper subset of the naturals. They're contained within the naturals, but they don't make up the whole set. We can write this relationship in the following way. Now it's worth noting that when we deal with finite sets, a proper subset is always smaller than the set itself. For example, the set of the first 5 square numbers, 1, 4, 9, 16, 25, has cardinality 5. If we consider one of its proper subsets, for example 1, 4, 9, we see that the cardinality is less, in this case 3. and the same holds for other proper subsets. In fact, for any finite set with n elements, a proper subset can have at most n-1 elements. It can never be equivalent in size to the whole set. This reflects a deeply rooted intuition about finite collections of objects, the idea that the whole is always greater than the part. And so our instinct screams at us that the same must surely hold for the set of even numbers, which is a proper subset of the natural numbers. In other words, we expect the cardinality of the evens to be less than the cardinality of the natural numbers. But according to Cantor's rule, they are not, and the reason is very simple. If we list all the natural numbers, then we can put the even numbers in a perfect one-to-one correspondence. We simply match the natural number n with the even number 2n. In this way, every natural number has a unique even partner, and every even number is used. Nothing is left unmatched. And so, by Cantor's definition, the set of even numbers is the same size as the set of natural numbers. Both have the same cardinality. And this shows that the principle that the whole is greater than the part fails for infinite sets. Infinity doesn't play by those rules. Infinity can, in some real sense, be cut in half and still remain the same size as the whole. And here's the thing. Once you start applying Cantor's logic, it's hard to stop. For example, what if we thin out the naturals even more and consider the set of perfect squares, s equals 1, 4, 9, 16, 25, and so on. This set is generated by taking the natural numbers and then squaring them. If we look at the distribution of the square numbers, it's clear that they get further and further apart as you go along, leaving ever larger gaps between them. So surely this increasingly thin subset of the naturals is smaller. But remember, Cantor said that two sets are the same size if we can pair them, and here we can. We simply map each natural number n to its square, n squared. So if we write out the natural numbers, then 1 pairs with 1, 2 with 4, 3 with 9, 4 with 16, and so on, with n pairing with n squared. Every natural number produces exactly one square number, and every square arises from exactly one natural number. So, against our intuition, the perfect squares are just as numerous as the natural numbers themselves, and we can write that as the cardinality of the squares is equal to the cardinality of the naturals. Okay, so let's keep going, but this time, instead of thinning things out, let's expand. Let's take the natural numbers and add 0, and while we're at it, let's throw in all the negative whole numbers as well. That gives us the set of integers, which we label z. Now, here's another example of where your intuition should start yelling at you. The naturals march forward forever in one direction, but the integers stretch out in both directions without end. Surely that has to be bigger. How could a line that runs infinitely forward possibly match one that runs infinitely forward and infinitely backward? And yet, once again, Cantor's reasoning shows that it can. If we start by listing the natural numbers, we can then use a zigzag pairing. We start with 0 and pair it with 1, then move to the right and pair 1 with 2, then move to the left and pair -1 with 3, then right again to pair 2 with 4, and then we simply keep going back and forth without end. Every natural number gets used and every integer gets a partner. So the seemingly impossible happens once again, and we conclude that the cardinality of the integers is the same as the cardinality of the natural numbers. Even when intuition suggests that the size of the infinite set has somehow doubled, and even though the natural numbers are clearly a proper subset of the integers, Cantor's logic shows otherwise. Hopefully by this point, Cantor's idea is clear. The size of an infinite set isn't determined by how much space it seems to occupy or how tightly its elements cluster. What matters when asking whether two sets are the same size is whether you can set up a perfect one-to-one pairing between them. And when that pairing is with the natural numbers, we call the set denumerable or countably infinite. Under this definition, the even numbers, the squares, and the integers are all denumerable. They all share the same cardinality as the natural numbers, and as shocking and counterintuitive as this feels, what came next shook the very foundations of mathematics and marked one of Cantor's first truly groundbreaking discoveries. I was recently helping my nephew revise for his maths exam on quadratic equations. Like most teenagers, he spends more of his time on his phone than reading his textbook. So I thought, why not build a revision app that he actually wants to use? That's when I discovered the true power of Lovable. Lovable lets anyone, whether you can code or not, create and design apps and websites simply by chatting with AI. You describe your idea and within minutes the app is built. Front end, back end, everything. Production ready straight away. It's perfect for individuals with ideas and for companies who need prototypes or internal tools fast. For my nephew's app, I just typed create a maths revision app for quadratic equations with timed quizzes and a leaderboard, and in minutes the full app was ready. Want to tweak colours or text size? Just click and change them right on the page. If you can code, you can customize even further. And when you're happy, hit publish, and it's live instantly. Lovable saves hours of work and makes building apps accessible to anyone. It's already one of the fastest growing startups, trusted by millions of people, backed by over $200 million in funding and valued at $1.8 billion. So whether you're growing a business or launching your first idea, why not give it a try for yourself? Go to lovable.dev and use my code PhysicsYT20 for 20% off. That's lovable.dev, code PhysicsYT20. Okay, so let's get back to the maths. The infinite set that became Cantor's next target was the set of all rational numbers, usually written as Q, which consists of every possible fraction built from the integers. Numbers of the form a over b, where a and b are integers and b is not zero. Familiar numbers like these. And of course, all the integers themselves are rational, since any whole number n can be simply written as n divided by 1, and that is a ratio. Now it's worth emphasising just how overwhelming this set really is. Consider the real number line and then look at the short stretch between 0 and 1. If you pick any two fractions, no matter how close, you can always squeeze in another, and then repeat, each time picking a pair of fractions and finding a fraction that lies between them. And you can continue this process without end. Between any two rationals, however close, lies an infinity of others. No matter how far you zoom in, the rationals are always there. By comparison, the natural numbers march along in evenly spaced steps, leaving vast empty gaps between them. Once again, if you rely on your intuition, you would surely expect Q to form a larger infinity than n. But Cantor said no, and his reasoning is simple and breathtaking. He began by showing how to turn the positive rationals into a list. You start with only the positive rationals, which are numbers of the form p over q, where p and q are natural numbers, then arrange them into a grid where you place the fraction p over q in the pth column and the qth row. So for example, 1 over 1 is at the top left, 2 over 1 sits to its right, then 3 over 1, and so on across the top row. Then in a similar fashion, we can populate the second row and then continue row after row, creating an infinite grid of rational numbers. The entire infinite collection of positive rationals sits inside this infinite grid. Now comes the clever part. Cantor traced a zigzag path through the grid. Start at 1 over 1, then move to the right to 2 over 1, then cut back to 1 over 2, and then down to 1 over 3. Then diagonally upwards to 2 over 2, and then 3 over 1, and then repeat the pattern. So next to 4 over 1, then back down along the diagonal to 3 over 2, then 2 over 3, and then 1 over 4. And keep going, each time zigzagging back and forth without end, covering the whole grid. And if we run this process again, we see that this path creates a sequence, a single ordered list of the positive rationals, guaranteed to cover every single positive rational. And here's the key. Whenever the path lands on a fraction that reduces to one you've already listed, like 2 over 2 and 3 over 3, which are just 1, or 2 over 4, which is a half, or 4 over 2, which is 2, you simply skip it and move on. In this way, every positive rational in lowest terms appears exactly once, so there are no repeats and no omissions. Next, we can line up the natural numbers with the rationals. The first natural with the first fraction, the second natural with the second fraction, and so on. Every rational number gets its own slot, and every natural number is used exactly once to label it. In this way, Cantor constructed a genuine one-to-one correspondence between the natural numbers and the positive rationals. And with a little extra care, the idea extends to all rationals, positive and negative. Following the exact same process, we can create an ordered list of the negative rationals. And then, just as we did with the integers, we can create a new list alternating between the positives and negatives. One positive, then its negative, then the next positive and the next negative, and so on, with 0 placed at the start. In this way, every rational number, positive, negative, or 0, finds its unique place in the sequence. And we can then line this up in a one-to-one way with the natural numbers. So despite their dizzying density, infinitely many squeezed between any two others, the rationals are countable, or in Cantor's language, they are denumerable. The rationals have exactly the same cardinality as the natural numbers. Infinity doesn't care how tightly packed things are, or how many gaps there seem to be. What matters is whether you can build a systematic pairing, and for the rationals you can. And that's the shock. The rationals, which seem to swamp every inch of the number line, turn out to be no bigger, in terms of cardinality, than the simple counting numbers. Now, given that every infinite set that we've looked at so far can be put into a one-to-one correspondence with the natural numbers, they have all been denumerable. So it's natural to suspect that every infinite set is denumerable. Cantor put that to the test by turning to a set so vast it contains all the previous ones as subsets. That set is the set of all real numbers R. You can think of the real numbers as all the points on the continuous number line. In other words, every possible decimal expansion. Numbers like 0.5, 2.75, minus 3.14159, or the square root of 2. Any position you can specify on the continuous number line by writing down a decimal, finite or infinite, corresponds to a real number. The real numbers include everything we've already met, the naturals, the integers, the rationals, but they also include something stranger, the irrationals, numbers like the square root of 2, pi, and the constant e, whose decimal expansions go on forever without falling into a repeating pattern. And if you put them all together, the rationals and the irrationals, you get the continuum, the real number line, filling every point without gaps, stretching endlessly from negative infinity to positive infinity. So here's the question that made Cantor famous. If the rationals, dense as they are, can be listed, what about the reals? Can every real number be put into a neat one-to-one correspondence with the natural numbers? Or does this infinity escape our ability to count? To make things simpler, we're going to take the real number line and then restrict our attention to the interval between 0 and 1. If we can show that the real numbers between 0 and 1 cannot be counted in the way outlined by Cantor, then the whole set of real numbers is uncountable too. Cantor's ingenious strategy was to begin by assuming that all real numbers in the interval can be denumerated and written out in an infinite sequence, and then show how it's possible to construct a new number that is guaranteed not to appear anywhere on that list. That would give us a proof by contradiction. If we succeed in finding such a number, then the original assumption that the list contained all of them must be false. Before we tackle the infinite case, it's worth warming up with a smaller concrete example. Imagine you had only a finite list of rationals, say 4 numbers written to 4 decimal places. Now let's try Cantor's trick. We construct a new number that has an integer part equal to 0, and then we choose the first decimal after the 0 so that it's different from the first decimal of the first number in the list. For example, the number 3. We then do the same for the second decimal, third decimal, and fourth decimal, and we end up with a new number, 0.3547. Notice what's happened. This new number differs from the first number in the first decimal, from the second number in the second decimal, from the third number in the third place, and from the fourth number in the fourth place. So it's guaranteed not to be on our original list. So how can we extend this idea to the case of infinitely many numbers? Well, let's imagine we try to write down every real number in the interval between 0 and 1 in a table with the first number written as 0.A1, A2, A3, A4 and so on, the second number as 0.B1, B2, B3 and so on, and then each row another real number in decimal form, where the lowercase letters represent the digits after the decimal point. And it's important to emphasise that we assume that this table contains every real number in the interval. And now comes Cantor's stroke of genius. We take the digits that lie along the diagonal of this table, A1 from the first number, B2 from the second, C3 from the third, and so on, and we use them to construct a brand new number. The new number has integer part 0, and then for the first decimal place, we choose a digit which we label A, and we make sure that A is different from A1. For the second decimal place, we choose a digit B, such that B is different from B2. For the third decimal place, we choose a digit C, with C different from C3, and we continue this way forever, always ensuring that our chosen digit differs from the digit on the diagonal. Then, to avoid complications, such as the fact that 0.9 recurring equals 1, we simply agree never to use 0 or 9 when making our choice of decimals. This technicality changes nothing about the power of the argument. The result is a new number of the form 0.A, B, C, D, E, F, and so on. And here is the remarkable part. By construction, this number does not appear anywhere in the original list. It differs from the first number in at least the first decimal place, from the second number in at least the second decimal place, and the third number in at least the third decimal place, and so on without end. And therefore, by construction, this new number cannot appear anywhere on the original list. This contradicts the assumption that we had already listed all of the real numbers in the interval between 0 and 1. And so we see that no matter how one tries to arrange the real numbers between 0 and 1 in a list, there will always be at least one missing. And if there is no complete list, then there is no way to pair off the real numbers one-to-one with the natural numbers. A one-to-one correspondence requires that every element of each set appears exactly once, with nothing left out. Cantor's construction shows that the moment you try to build such a correspondence, you can always find a real number that is excluded. And therefore, the assumption that the reals between 0 and 1 can be denumerated collapses. Cantor's simple but devastating construction shows, in a single stroke of genius, that the set of real numbers in this interval is not countable. And since this small interval of the entire real number line is uncountable, it follows that the entire set of real numbers is uncountable as well. And so the conclusion is striking. Unlike the naturals, the evens, the squares, the integers, or even the rationals, the reals form a strictly larger infinity. At first glance, this conclusion feels almost unbelievable. Now, we began by proving that even the narrow interval from 0 to 1 cannot be listed and therefore cannot be paired with the naturals, and as a result, it already holds a larger infinity than the naturals. But this only raises another puzzle. Surely the size of the reals should depend on how much of the line we take. Intuition screams that the whole real line, stretching from minus infinity to plus infinity, must somehow be bigger than that tiny slice between 0 and 1. But Cantor showed that our intuition once again is wrong. Imagine taking the number line and then lifting the interval 0 to 1 up above the number line and bending it into a U-shape. Then place a point midway between the open ends, and from that point draw rays downwards through the U so that they hit the real line. As the ray sweeps back and forth, every point of 0 to 1 is projected to exactly one point on the line below, and every point on the line receives exactly one partner. The result is extraordinary. The short segment between 0 and 1 can be put into a one-to-one correspondence with the entire real line. Now we can make that pairing completely explicit with a formula. Consider the function f of x equals tan of pi times x minus 0.5. As x moves from just above 0 to just below 1, the angle pi times x minus 0.5 sweeps from minus pi over 2 up to plus pi over 2 radians, and the tangent function rises smoothly from negative infinity to positive infinity, hitting every real value exactly once along the way. We can see this explicitly if we plot the function. For any x between 0 and 1, there is a perfect one-to-one correspondence with a unique real number, and we can generalize this approach to any size slice. No matter how big or small the slice, any interval of the real line already contains the full infinity of the continuum. Even the tiniest finite stretch is packed with a non-denumerable infinity of points. Once again, the ancient rule that the whole must be larger than the part collapses in the face of infinity. Now, it's worth noting that Cantor's very first proof of this result appeared in 1874. That early argument used the mathematics of analysis and a subtle process of nested intervals. Only later, in 1891, did he publish what is now one of the most famous mathematical papers ever written, the one containing the diagonal argument we've just seen. Okay, so what next? Well, having revealed this new hierarchy of size, mathematicians came to describe it using special symbols. The cardinality of the natural numbers is written as Aleph naught, a symbol Cantor introduced to denote the size of the naturals, and the cardinality of the real numbers, the continuum, is commonly denoted by C. With these symbols, the discovery can be summarized in a single inequality. Aleph naught is less than C. For centuries, mathematicians had been uneasy even speaking of infinity as a completed object, and now Cantor had shown something that defied all intuition. There are different sizes of infinity, and the infinity of the real numbers is strictly larger than that of the naturals. But the revelations didn't end there. Cantor was able to follow the logic of his newly developed set theory to uncover even more startling insights about the newly uncovered world of the infinite. To do this, he leaned on a simple but powerful observation. Suppose we're dealing with two infinite sets A and B. If we can write down both A and B as a list, lining up its elements one by one with the natural numbers, then we can weave the two lists together into a single new list by alternating the two. The result is a new set C that contains every element from both sets. If the same element appears twice, we simply skip the duplicate, as we did before. In the language of sets, this observation can be put more formally. If two sets P and Q are denumerable, then their union is also denumerable. We can always build a one-to-one correspondence between the natural numbers and the union, simply by interleaving the two existing enumerations. Okay, so let's now put this to use. Suppose, for the sake of argument, that all of the irrational numbers could be listed. We already know that the rationals can be listed using the zigzag trick we encountered earlier. Then, by using the interweaving method we just discussed, we could combine the two lists, alternating terms from each. The combined list of rationals and irrationals would then contain every real number, since the reals consist of all rationals together with all irrationals. But as we've already seen, Cantor proved that no such list can exist. This contradiction shows that the irrationals cannot be listed. They are uncountable. And so the rationals, infinite though they are, form only a thin dusting along the number line, while the irrationals fill in everything between. Mathematicians often say that most real numbers are irrational, and now we can see why. The familiar fractions, dense yet countable, are just scattered points in a vast, uncountable ocean of irrationals. And Cantor wasn't finished. He now turned to another division of the real numbers, algebraic versus transcendental. Algebraic numbers are those that solve polynomial equations with integer coefficients. In other words, any number that is a root of a non-zero polynomial of the following form, with all the a's integers. If some number x makes such an equation true, that x is called algebraic. Now, this definition might sound abstract, but the examples are very familiar. Every rational number is algebraic because any fraction p over q is the solution of the linear equation qx minus p equals 0. Furthermore, a number such as the square root of 2 is algebraic since it solves x squared minus 2 equals 0. The cube root of 5 is algebraic since it solves x cubed minus 5 equals 0. Even the golden ratio, phi equals 1 plus the square root of 5 all divided by 2 is algebraic since it satisfies x squared minus x minus 1 equals 0. So algebraic numbers cover a vast range of the familiar territory of mathematics: fractions, roots, quadratic surds, and more. The transcendental numbers, by contrast, are the apparent outsiders, numbers that cannot possibly be the root of any such polynomial equation. They quite literally transcend algebra. And concrete examples do exist. Charles Hermite proved that E is transcendental in 1873, and Ferdinand von Lindemann proved that pi is transcendental in 1882. Earlier, Leonhard Euler had suspected they must exist, and Joseph Liouville constructed explicit examples. But in the 1870s, they were still rare, and so it was tempting to think of them as scattered curiosities rather than the rule. Cantor turned that picture on its head. Since all real numbers can be categorized as either algebraic or transcendental, then if you can prove that the algebraic numbers are denumerable, then since the real numbers are non-denumerable, it follows that so too must be the transcendentals. And this is exactly what Cantor did. He proved that the algebraic numbers are countable. The reasoning is clear once you see it. Each polynomial equation is determined by a finite list of whole number coefficients. All finite lists of integers can themselves be put into a list. They are countable. So all such polynomials are countable too. And since each polynomial has only finitely many roots, all those roots taken together can be counted. With some patience and bookkeeping, every algebraic number eventually appears. In short, the set of algebraic numbers is denumerable. Now combine that with Cantor's earlier discovery. If the reals are uncountable, but the algebraics are countable, then the rest of the reals, the transcendentals, must be uncountable. The transcendentals don't just exist, they dominate. They are not the exception, they are the overwhelming majority. As the mathematician E.T. Bell put it so poetically, the algebraic numbers are like stars scattered against the blackness of the night sky, but the darkness itself, stretching boundlessly in every direction, is the firmament of the transcendentals. The impact of Cantor's discoveries was seismic. Infinity ceased to be a vague abstraction and became a landscape that could be mapped and compared. He showed that not all infinities are equal, but reception to his work was mixed. Richard Dedekind appreciated its depth and urged him on. By contrast, his former teacher, Leopold Kronecker, a staunch finitist, rejected Cantor's methods and became a fierce critic. Yet, despite the hostility, Cantor pressed on. With Dedekind's encouragement, he continued to develop his ideas. Cantor had shown that some infinities, the naturals, the evens, the squares, the integers and the rationals all share the same size, Aleph naught, yet the continuum leaps beyond them, a strictly larger infinity. For most mathematicians, that discovery alone would have been a lifetime's work. But Cantor was not most mathematicians. He became convinced that beyond the continuum lay an endless hierarchy of ever greater infinities. And that is where we'll go in the next video, exploring the infinite ladder of sizes of infinity that rise beyond the continuum. And we will face a question so deep that even today it is undecidable. The continuum hypothesis. Is there some intermediate size of infinity between the infinity of the naturals and the larger infinity of the continuum, or none at all? But for now, I will let Cantor have the last word. My theory stands as firm as a rock. Every arrow directed against it will return quickly to its archer. How do I know this? Because I've studied it from all sides for many years. Because I've examined all objections which have ever been made against the infinite numbers. And above all, because I have followed its roots, so to speak, to the first infallible cause of all created things. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.